And then the addition, I think, which I can make to the title of the workshop is to stress that the dynamos are not only over there, down here, but all around us. We are living within a giant dynamo machine. I will be talking about magnetic fields, not necessarily dynamos. You know, dynamos don't exhaust the whole richness of life as we know it. And there are also many other interesting effects where magnetic fields are involved. And I will move more or less slowly. I hope I will have an additional lecture, Axel, right? Would it be possible?
Sure, yes.
First, to establish the scene, to discuss in this first part, I will be talking about galaxies and galaxy clusters from astrophysical viewpoint, or rather physical viewpoint, as I want to establish the main parameters of galaxies and galaxy clusters, why these parameters are as they are. Very much similar to what Chris was doing with planets. Just to establish the background, to describe the scene. Then I will continue in part 2 to observations of astrophysical magnetic fields and also velocity fields. How we know the velocity fields and magnetic fields in these very often very remote objects. And then finally there will be 2 parts, one about the origin of magnetic fields in galaxies and then about galaxy clusters. This is my plan. And since my lecture today is sort of about 24 hours before planned, right? I consider it to be a good excuse for me to be badly prepared. So, but I would appreciate it if you ask your questions straight away when they arise. Don't hesitate interrupting me. It will only make my task easier if you will be asking me your questions straight away. So, I will first talk about 2 types of galaxies, spiral and elliptical galaxies. The section about spiral galaxies will be significantly longer just because these objects are much more physically diverse, much more physically rich. More interesting phenomena occur in spiral galaxies. And then I will end with describing galaxy clusters. My plan today, for today's lecture, is to reach this point, to finish this part. If I will be unlucky and too slow, at least spiral galaxies we shall have discussed in 90 minutes. So, I will be using CGS fields, stubbornly and perhaps unreasonably. So, magnetic fields will be measured in Gauss, or rather micro-Gauss in galactic scales, 1/1000th of a Gauss. 1/1000th of a Gauss is 1/10 of nanotesla, if you prefer MKS units. Some physical constants, no need to remember them unless you start making estimates. I will be using very often unit length, quite convenient in galactic astronomy. It's 1 parsec, parallax second. Parallax second. It's the distance from which the angular size of the Earth orbit is exactly 1 second apart. It's roughly the distance to the nearest star, nearest external star next to the Sun. So it's about 3 light years, or 3 times 10 to the 18th centimeters, divided by 100 to get meters. I will be using the solar mass radius and luminosity. It's these units are given here. Astronomers, following the, I think, spectroscopists, use this notation for various ions. H with Roman 1 means neutral hydrogen. H with Roman 2 means singly ionized hydrogen, that is a proton. And so, subtract 1 from this Roman numeral, you will get how many electrons have been stripped off a given atom. So, C4 means triply ionized carbon. Mostly I will be mentioning H1 and H2. This will be most often used. Most of the species. There are a few excellent books and modest reviews on this subject. If you really want to know more about galaxies, I myself found at some point very useful this semi-popular book of Roger Taylor, it's an excellent book. It's an excellent reading. It is a scientific popular book, but aimed at specialists, at people with physical background. So it's exactly for people like us. If you want to learn more about galaxies, this is an excellent introduction. Then there was a very short and very informative textbook on interstellar medium, again written by physicists, so that they talk about physics rather than zoology. And more reference can be found in our recent review, about 40 pages, whose topics are very similar to what I am going to present today. So, galaxies, first of all, are understood as collections of stars. For a very simple reason. With optical telescopes, if you observe galaxies in optical range, you will first of all see stars. So, and stars do contribute significantly to the mass of the galaxies. But perhaps no less important is the fact that the space between stars is filled with partially ionized plasma, the solar medium, which will be our main subject. It is, in most cases, in most regions, collisional, so it behaves like a magnetized electrical conducting fluid. There are also relativistic particles, cosmic rays, and a little bit of dust. These are mainly silicates, ices. They play an important role in visualizing various dynamical aspects of interstellar gas, but as physical constituent, then the dust isn't that important. Clusters of galaxies are the largest isolated objects we know in the universe, gravitationally bound objects. Their collection of galaxies, about a few thousand galaxies per cluster. And again, the space between the galaxies is filled with intergalactic gas. We shall say, I will provide estimates of the parameters later. And galaxies can be conveniently classified according to this scheme. It was probably historically the first scheme of classification by Edwin Hubble. After that time, since that time, more complicated classification schemes were introduced, but this still remains one of the most successful. Here, the classification of galaxies, the reason is that the classification of galaxies in this scheme reflects their physical differences. So the classification based on physical differences. So the world of galaxies consists of, it's convenient to start with elliptical galaxies. These are denoted with E0. These are almost featureless, structureless, almost spherical collections of stars and gas. Then there are other types of elliptical galaxies, which become flatter and flatter as you move along this diagram. E7 are the flattest of elliptical galaxies. So they become flat not because they rotate. These are triaxial ellipsoids of stars, and they are oblate just because the velocity dispersion of stars in these galaxies is anisotropic. Their rotation is negligible. They almost don't rotate, just clumps of matter. Then there is this is why this diagram is called pitchfork diagram. Then there is a world of spiral galaxies, which are represented by two main types. These are normal spiral galaxies, and these are barred spiral galaxies. All barred spiral galaxies have this strongly non-symmetric feature at the centers, called bar. Yes, please, Michelle.
What causes this anisotropy?
Sorry?
What causes this anisotropy in E7?
As far as I understand, they haven't, they are relaxed thing. It's just a, relaxed state of collisionless system. These are collisionless systems.
So you mean E0 is not as relaxed as E7?
Well, he said they are relaxed.
They are relaxed. Yeah. They are relaxed. They are all relaxed.
Yeah,
they are the oldest galaxies. They are much older than.
So what is the difference?
Stronger anisotropy of velocity dispersion here.
The reason?
The reason nobody knows.
What they are relaxed. But, so for example, violent relaxation.
No, no.
It leads an isotropic, right?
No, no, nobody knows why some galaxies have anisotropic velocity dispersion and others don't.
Yes, because it is the question about the origin, formation of galaxies, right? Which remains an unsolved problem.
But E7 may be in a higher energy state than E0. So you might expect if you were able to dissipate energy, you would gradually evolve to E0. Is that true? No?
I don't know. I still don't know. Oh, well, I guess the question to this answer is no. It's just my ignorance which prevents me from answering. But I agree that anisotropy, it cannot be the state with the minimum energy. It can be completely relaxed state.
No, because these are collision-less systems.
Yeah, yeah.
So
They don't
evolution is
have
slow.
isotropic pressure necessarily. And why they relax to anisotropic dispersion, I don't think is known.
But I would speculate that, for example, there is a Donald Lyndon Bell. At some point in the 70s, he made almost a revolution by the idea of violent relaxation, where he introduced collective processing collisional systems, which allowed to explain why inord or in some old parts of spiral galaxies are relaxed at all. Because relaxation in collisionless system can be quite slow. So my guess would be that after violent relaxation, they come to quasi-relaxed state, but anisotropy remains and it evolves very slowly. But it's only my guess. But I can check from Wikipedia.
You can write a paper.
So, the right
Based on Wikipedia.
So these galaxies are called spiral for obvious reason. Look at these beautiful spiral arms in these photographs. All these objects, barred or normal spiral galaxies, they are all flat. They have a shape of roughly of a hand palm. And they are flat because they rotate. Unlike these elliptical galaxies, all these galaxies rotate fast. And the further you move in this direction, the more important becomes the rotation. This is why they are flat. And then, as with any other classification, there will be always something which doesn't fit anything. Similarly with galaxies, there are galaxies which don't fit this classification. They are called irregular galaxies. Indeed, they are quite irregular. Sometimes they have traces of spiral structure, sometimes no. Very often they are also resemble in shape elliptical galaxies, but they contain many young stars as spiral galaxies. These galaxies, elliptical galaxies, their stellar populations are very old. This is why they look yellow. Spiral galaxies have large numbers of young stars. The process of star formation still continues, which makes them especially attractive from physical viewpoint. They are really interesting and living objects. These are sort of fossils.
Sorry, what is the peculiarity of SBO type or SO type?
SO, they already rotate fast enough so that they have a thin disk. But still, the quasi-spherical subsystem is very strong.
So there are no spiral arms.
Sometimes there are spiral arms, but they are rather weak. So if elliptical galaxy looks like this, and spiral galaxy looks like this, if seen from the edge, as all galaxies look like this. So relatively weak disk and very strong quasi-spherical system. And then here in the disk there can be some spiral structure.
Okay, but one could say that the halo is dominating there?
Yes. Most of the mass sits in the quasi-spherical component. This is the galaxy NGC 6946. It's SB type galaxy. So we are here in the middle of this branch of the pitchfork. It's seen from the edge. The inclination is 89 degrees. So it's just 1 degree away from being seen just exactly edge on. and we can see how thin is the disk. And here we can conveniently see the structure of this galaxy. This is a stellar disk. You can see, if you see the quite weak light, it extends quite far. This dark lane is exactly that interstellar dust. It is concentrated in a very thin disk, and when you see edge on, it obscures the stellar light. So, yes?
Can you tell in this case NSB or NSA?
From the relative sizes of bulk of this quasi-spherical, system of old stars in the middle. From the relative sizes. So, this is the stellar disk, very pronounced, strong, powerful disk. Then there is a quasi-spherical part, which resembles in many respects a small elliptical galaxy. It consists of very old stars, and it's quasi-spherical. It doesn't rotate very fast. Velocity dispersions isotropic in spiral galaxy. Isotropic. Then, further beyond, we cannot see it because the stellar density in the halo are relatively low. But there is a halo of roughly that size. Globular clusters, the oldest stars in spiral galaxies, are mainly in this system, which we can hardly see in this photograph. But obviously, if you make exposure deeper, then you will see this system. And then all this stuff is within the dark matter halo. Dark matter is something which is nobody knows what it is. This is a part of galaxies and other astrophysical objects which only manifests itself through gravitational interactions. It's one of the major problems. There is no doubt that there is a gravitational force produced by something which we cannot see. I will discuss the evidence for that later. What is the physical nature of this dark matter? Nobody knows, and I think, well, it must be a Nobel Prize sort of question. Those who will be able to explain the physical nature of dark matter is definitely not the Nobel Prize level result. But we know about the existence of dark matter here mainly from the gravity field, which you can measure by measuring velocities of gas and stars in this galaxy. So all this is surrounded by a halo of gravitating mass. This is a similar galaxy. It's SC galaxy, right? M51, SC. So this is a galaxy, let's return back to here, of this type, with even better pronounced spiral structure. Seen almost face on, this galaxy is inclined to the line of sight by just 22 degrees. So what? Something like that. This is how we see this galaxy. Here you see this beautiful spiral pattern. This is why these galaxies are called spiral galaxies. This is a companion. This is a small galaxy which is in a gravitational interaction with M51, this companion galaxy. So, the Hubble classification, the various parameters of galaxies and how they vary with the spectral, with the Hubble type. For early type galaxies, these elliptical galaxies are called early type galaxies, and these are called late type galaxies. The nuclear bulge is this quasi-spherical formation in the center, this stuff. Elliptical galaxies all consist of bulge. SC galaxies have very small bulge, and they are all intermediate states. The spiral arms, they are not present in E0. Look at this material. S0 have no spiral arms, sorry. So there is a disk but without spiral arms in S0. And then open and clumpy spiral arms in SC galaxies. Gas, little rarefied hot gas in elliptical galaxies, and about 10% of the total mass comes from the gas in SC galaxies. Young stars are not present in elliptical galaxies and are widespread in SC galaxies. Stars are old in elliptical galaxies and many young stars in spiral galaxies. Spectral type, G means reddish, solar type stars, right? Red or yellow stars, old stars. And F are very bright, massive blue stars, recently formed. The age of these stars is much larger than the age of stars of this type. The color changing from red to blue. The mass elliptical galaxies, some of them are really giant, 10 to the 13 solar masses. Spiral galaxies are less massive, and irregular galaxies can be really very small, just 100 million stars. Elliptical galaxies can be very luminous, and there are really big, giant elliptical galaxies. And spiral galaxies are usually less and less luminous. So this table gives clearly the reason why Hubble's classification is so successful, just because it is based on physics. It reflects the changes in the physical parameters of galaxies. So let's talk about spiral galaxies first. Here is a selection of nearby spiral galaxies. M51 familiar to us, 22 degrees, and GC891, almost edge on. M33, very interesting galaxy, which has its SC type. Look how clumpy are its spiral arms. And this NGC253 is again seen almost edge on. These codes represent the numbers of these specific galaxies in different catalogs. M stands for the catalog of Messier, which was compiled in 18th century, I think, right? By French astronomer Messier. At that time, people were mostly interested in observing comets, which were believed to be important objects, sometimes carrying fates of human beings with themselves. So people were interested in comets, and Messier made a catalog of bright objects in the sky, which are not comets, therefore do not deserve being observed. And amazingly, almost all objects in his catalog are very interesting galaxies or nebulae or stellar clusters. This NGC stands for New General Catalog. It's a more modern catalog of galaxies, which is extensively used now. These are a few photographs of barred spiral galaxies. Look at this bar here. Look how beautiful. Huge bar, also here. And look at the spiral arms. They start at the ends of the bar. This bar, which produces non-symmetric velocity field, is believed to drive the spiral pattern in these galaxies. The origin of the spiral pattern in these galaxies is not quite clear. Even there is an obvious reason why there should be deviations from axial symmetry in the form of spiral arms. There is this bar. But what drives the spiral structure here isn't quite clear. And surprisingly, you might think that because of this bar should be something again like a triaxial ellipsoid, like a cucumber, right? Not at all. These galaxies, when seen edge-on, are as flat as these galaxies. So this bar is flat, in fact. When we see it face-on, it looks like a hand. When you see it edge-on, it's very thin. It's very interesting, very interesting.
How often are the spirals trailing?
All of them are trailing.
All of them are trailing.
The examples of leading spirals are very rare. And usually they occur where there is an explicit reason why this can, for example, strong tidal interaction with a neighbor. So, to my knowledge, each time when there is a suspicion that the spiral arms are leading, always have a specific reason. Moreover, this is the way people decide in what direction the galaxy rotates just from direction of spiral arms, assuming that they are trailing. And as far as I understand, this assumption never failed.
So are there any spirals which are leading?
Yeah, there are a couple of examples. Strongly interacting systems. Again, it's not clear how transient are these structures. This can be transient structures, these leading spirals. So, from the viewpoint of a poor theoretician, this diagram shows almost everything that we need about galaxies. So, there is a stellar disk, a stellar bulge, together with dark matter, which surrounds everything. They produce the gravity which keeps everything together. It's a self-gravitating system. In this potential well, there is a interstellar gas whose thickness increases with distance from the center. We shall discuss it later. It's more or less obvious, right? If the pressure in the gas is more or less constant, say its temperature is more or less constant, turbulent pressure is more or less constant, then gravity rapidly decreases outwards because it's a self-gravitating system. The potential well is the deepest in the center. If the gravity becomes weaker, the disk spreads wider, and so its scale height increases with distance from the galactic center. If trying to show the Milky Way in this form, then our sun will be at about somewhere near to the outer parts of the galaxy, at the distance, if the whole radius of the galaxy is, say, something like 12, 15 kiloparsecs. The sun is the distance of about 8 kiloparsecs, 8, 10 kiloparsecs from the center. The typical radius of the disk is about 10 kiloparsecs. The typical thickness of the stellar bulge is half a kiloparsec. This is the aspect ratio. Half divided by 10, what? It's 5%, right? It's a really very thin disk. It's a really very thin disk. The typical density, average density of the interstellar gas is about 1 particle per cubic centimeter. So in a volume like this, you have 1 hydrogen atom on average throughout galaxies. The typical temperature is 10,000 kelvins, but these both are very crude averages. The ranges of variation are enormous. Locally, the density of interstellar gas varies by factor of 1,000. There are very dense clouds where stars are being formed, and there are very dilute and hot regions where the density is 1,000 times less than the average. Likewise, temperature. These dense regions are very cool, just 10 degrees Kelvin, and these rarefied regions are very hot, million kelvins. And if you multiply 10 to the minus 3 density of hot region by its temperature, it will be pressure, right? Density times temperature is pressure. You will get 1,000 with these units. Also here it's about 1,000. So roughly, the whole system is in rough pressure equilibrium. Oh, no need. These are just numbers referring to the Milky Way parameters. So this is the view of the Milky Way. We are living inside this object, and this is the infrared image of the sky. Here you see the galactic center, and the bulge is here, and this is the galactic disk. So this is sort of a view of the Milky Way from almost outside. Rotation. As I said, spiral galaxies are flat because they rotate fast. And rotation is a more or less readily observable feature of galaxies from Doppler shifts of spectral lines. And this is this dependence of radiation velocity on the distance to the galactic center is known as a rotation curve. They're measured for thousands of galaxies. A few tenths of rotation curves are shown here for many different galaxies. So, if you follow each individual curves, you will see that all of them, if not most of them, if not all, rare exceptions, right, become flat. They become flat with distance. It's a typical feature of spiral galaxies. The rotation velocity levels off becomes almost constant with distance. If distance is large enough from the center. The typical rotation velocity is what? A couple of 100 kilometers per second. So there are several types of rotation curves. They are all roughly similar. Look at this rotation curve, for example. You see, oh, by the way, rotational velocity V is equal to omega r, correct? Omega is the angular velocity of rotation. Omega of r times r. For r equal to 0, V must be equal to 0. What happens here? It doesn't go to 0 for a simple reason. It's not because the observers are silly and don't know that 0 times omega is equal to 0. It's just because many of these galaxies are believed to host black holes, massive black holes in the center, where the linear velocity of rotation grows very rapidly over a very short distance. So the rotation curve first grows very fast, very steeply, and then sort of levels at this the level between 200 to 300 kilometers per second. And remarkably, all these rotation curves are flat. First, differential rotation, it's differential rotation, right? Because if V is a constant, then omega of r will vary like 1 over r. So it's a well-pronounced differential rotation. Here, I plotted the rotation curve of the Milky Way. This is how it varies roughly. The sun is somewhere here. We are sitting somewhere here. And this is the shear rate, rotational shear rate for the Milky Way. Quite strong. It's that I plotted this just because in the dynamo models we shall need this variable, RP omega by dr, with the shear rate. The rotation curve is controlled by the balance of gravity and centrifugal force. So if phi is the gravitational potential, then in radius v squared over r centrifugal force must be balanced by the gravity force. Gravity comes from the Poisson equation. Rho g is the mass of is the density of the gravitating mass. A simple solution comes from a point-like mass distribution. If this rho g is a delta function at the origin, then phi will be minus gm over r. I differentiate it once. Here I get gm over r squared. I immediately get Kepler's rotational law, like in the solar system or in accretion disk. V is proportional to 1 over root of r. 1 over root of r. Not at all. It's not 1 over root of r. It's flat. Therefore, the flat rotation curve immediately tells us that the mass of galaxy, the gravitating mass, is distributed. And in fact, this observation of flat rotation curves was, I think, historically the first evidence of the dark matter. Because what people did, they became worried, of course, when they discovered that the galaxies don't rotate according to the Kepler's law. Then they carefully counted all the stars and calculated all the visible mass. And then solved this equation, obtained gravitational potential, and discovered that still they cannot obtain the flat rotation curve. And then people were forced to suggest that there must be something called dark matter which produces gravity enough to make rotation curve flat, but not visible in any other way. So these flat rotation curves of galaxies were historically, I think I'm not wrong, right? It was historically the first evidence of the dark matter.
Of course, strongest, but Zwicky had these clusters for which he was trying to estimate masses. Yeah, I think so. Right.
But at least widespread, it became widespread. And people people wanted to argue for the stability of the disk. They were trying to invoke Dark-Halo. I think Dark-Halo is an obstacle. Yes, but this is all, well, stability, no. All these theoreticians, they always invent something unpleasant. And silly. This is observational fact, which you must explain somehow. Stability or not stability, no. Okay. So, then now, this observation of rotation curves is in fact is used to understand how the mass is distributed within galaxies. So, first people observe the rotation curve, and then they start fitting various models. For example, they consider a model of the galaxy which consists of bulge, bar, stellar disk, gaseous disk, dark matter, and stuff like that. And then, if you look here, V squared is additive, right? So if one component produces certain gravitational potential, it will produce a certain V squared, and you can add them together. So you can decompose the rotation curve into the contributions of various constituents. I think this is for the Milky Way. So bulge and bar is this dashed line. Where is the dashed line? Here. So the bulge and bar produce at the distance of the sun about half of the total rotational energy. But then dark matter here, this is the dark matter. Oh no, wait a minute. Yes, this is dark matter. Contributes quite a lot, and the contribution of dark matter grows with distance. So, thus, from these observations, we have quite a good idea of how mass is distributed within galaxies, what is the galactic structure, which is very important. For example, when Chris was showing us the internal structure of planets, this diagram is in fact similar to the diagrams Chris was showing about the internal structure of planets. But there, you have to rely on very complicated experiments with the equation of state of the matter at enormous pressures and temperatures. So it's difficult. That information is difficult to get. Here, this similar information is much more readily accessible. It's almost directly observation. Next, now let's talk about the vertical structure of the disk. So we have discussed the radial structure of the galaxy. Now let's talk about the vertical structure of the gas disk. It is controlled to the first approximation by hydrostatic equilibrium. So there's, like any other gas, it produces pressure. There is a thermal pressure, nKT. There is turbulent pressure, 1/2 of rho v squared. V is the turbulent velocity. Magnetic pressure, cosmic ray pressure. All these contributions to the pressure are roughly of the same order of magnitude. Then d by dz of that, the vertical pressure gradient, must be balanced by the vertical component of gravity. Now we know how the mass is distributed, therefore the right-hand side can be calculated, right? We know the gravitational field of the galaxy from analysis like this. Now we shall use this to discuss the vertical structure of the galaxy. Clever, isn't it? So, and then you can solve for rho. This is a good convenient approximation to the gravity field close to the Milky Way. The dominant components are from the disk, it's this part, and from the halo, it's this part. So, if you can calculate express pressure in terms of density, you can solve for density. And the same density, but now in particles per cubic centimeter. Let's see how it can be done. Obviously, you have to, some assumptions have to be involved, just at least for illustrative purposes. So I will assume that all pressures are roughly the same magnitude. It was Gene Parker who first was bold enough to make this dramatic assumption, which turned out to be quite reasonable. So I will just collapse all these 4 components of pressure into one. Just said it's 4 times. Let's just see what will happen. I will assume that it's an isothermal atmosphere. Again, it's not a very better assumption. It's reasonably good. So temperature is constant. This means the speed of sound is constant, and then the speed of sound is constant. The turbulent velocities can also be more or less constant. And then, just in the simplest case, assume that G of Z is a constant, infinite slab. Temperature here is constant, only N is a known variable. Then you immediately solve this equation to get an exponential, isothermal atmosphere is an exponential atmosphere. And you will immediately calculate the scale height of this density distribution. It is expressed in terms of the gravity, which we know, turbulent velocity, which is observable. What is H2? H2 is the typical vertical scale of the dark matter distribution. And you get 200 parsecs, which is very similar to what is observed. Fantastic success. This means that we all sort of understand what's happening. even have made these dramatically strong assumptions, we end up with more or less reasonable result. It's very encouraging. It's very encouraging. This means that this path is worth improving. Now you can fine-tune all this stuff to get a better model. But the system is simple enough to allow reasonable modeling. Now, how this changes with radius? This equilibrium was, I solved this equation at fixed radius, right? But obviously this G depends on R, or on the cylindrical radius. All these variables, n perhaps T, B, rho, V naught, may depend on R. How this changes with radius? Let's look at this. Now, d by dz of P, of pressure, is rho gz. Gz is d phi by dz. And phi is obtained from the Poisson equation. Now, I want to solve this equation at different radii, where radius now will be a parameter. And there's a trick which I really like, really a clever way to solve these equations, suggested by Oort. He's a famous Dutch astronomer. He belonged to this generation of great astronomers who made galactic astronomy a part of physics rather than part of zoology, due to their work in the 60s and 70s. He was one of those great astronomers who really put galactic astronomy on a very solid physical basis. So, look what he did. From this equation, I can express d2 phi by dz squared, which is dz by dz, in terms of the density, which I know. I know the distribution of gravitating mass from the rotation curve, plus the radial part of the Laplacian. But gr is equal to minus d phi by dr, and this is related to the rotational velocity. This is my centrifugal balance. So this gr is known to me from observations. Then, if so, I can integrate this once. So on the right, gr is known, rho g is also known, and therefore there is nothing for me to solve. I just integrate this equation once, and I get gz in terms of the integral of observable quantities. So then I express this pressure as 4 times, say, turbulent pressure. Gz is given by this integral. If I have a flat rotation curve, if v is a constant, then this term is identical 0. It goes. And then a good approximation to the radial distribution of gravitating mass is an exponential. So roughly along the radius, gravitating mass decreases, mass density decreases exponentially. Then if rho g is an exponential, I will integrate over z, it will remain an exponential. So here I have an exponential of radius. This means the scale height will grow exponentially. Beautiful, right? So this is Zeldovich used to, unfortunately I couldn't find a good English translation of this maxim. The skill of a scientist consists on the ability of making complicated problems unnecessary to solve. And the problems you need to solve simple. Right? So don't solve complicated problems. Try to make it simple, retaining this the importance. This is what Oort has done. He solved the Poisson equation, and after that, this equation, without solving anything, just because he's clever. He used observational information here to solve the Poisson equation very easy. Just this integral. This is what clever people do. Because when I first, before I discovered this paper of Oort, of course I started solving first the Poisson equation as I was taught in the university. Eigenfunction expansions, Bessel's functions. I immediately realized that but my only goal was to derive this exponential behavior. And when I saw that there are all these infinite series, these Bessel functions, well, Obviously, exponential behavior is hidden somewhere there. But look at this beauty. Look at this beauty. So, the observations of Peter Haberle from Bonn, very recent observations of the neutral hydrogen layer in the Milky Way. Where are the observations? Average. Red line is the average over the northern and the southern hemisphere, galactic hemisphere. So this is what is observed. This is how the thickness of the layer increases with distance from the center of the galaxy. And this is the mass model calculated in exactly that way. This dots. Oh, look at this. Look at that. Not bad, right? I was really deeply impressed by this idea of solving for the hydro equilibrium and different radii this way. Very elegant, very direct and precise. Just hits the target. Just hits the target. And the key here is the use of additional information, observational information, so that in this Laplacian, in fact, you do know half of it from observations. No need to solve for this. This is known. This is known. Interstellar gas isn't just a one single quasi-uniform plasma. In fact, it is constantly agitated by supernova explosions. Supernovae are very massive and young stars. If the mass of the star exceeds something like 20 solar masses, then it evolves very rapidly at the time scale of million years. These are very massive, big stars. And at the end of the evolution, if I remember earlier what happens, they exhaust the nuclear fuel very quickly at the center. And then they first collapse because they lose pressure at the center. And in the course of the collapse, the temperature increases, a new chain of nuclear reaction starts, which leads, as often nuclear reaction do, to an explosion, which disperses most of the star over a large region, but the core which is left is in fact a neutron star. So neutron stars, pulsars, are formed in this supernova explosion. So each explosion contributes the energy of 10 to the 51st Earths into the interstellar medium. This is the amount of energy released in each explosion. At some point, I tried to make sense of this number. And I was preparing a talk, which was due just before Christmas, a few days before Christmas. And then I estimated how many Christmas dinners correspond to this energy. The result was still useless because it was so huge. I think it was enough to feed the whole population of the Earth with Christmas dinners every day for a few billion years. Something like it's a huge energy. Just a huge energy. So, what happens after any explosion? Remember, right, these photographs of these fireballs which develop after atomic explosion. Similar fireballs are produced by supernova explosions that they create bubbles of very hot, rarefied gas. Since it is rarefied, the density is very low, it cools very slowly. Because cooling, radiative cooling, occurs because of collisions between molecules, right? What happens is high temperature plasma, after collisions of particles, they radiate energy because there will be acceleration, R double dot. So the cooling is related to collisions. This means that the cooling will be depend as rho squared on the density because these are pairwise collisions. Density is low, therefore cooling is slow because the collisions are rare. This means that these hot regions, they have a very long lifetime, and before such a hot region can cool down to the normal state, another supernova will explode nearby, and then it will support this hot region. So the result is that this disk of gas looks like cheese with big holes of very hot rarefied gas. Moreover, supernovae do many other useful things. They produce an expanding blast wave. As soon as this blast wave, obviously this blast wave will carry very significant kinetic energy. About 10% of this energy goes into this kinetic energy. And this kinetic energy will be deposited into the surrounding medium. This will drive motions in the surrounding medium. And since the supernovae occur at quasi-random positions and times, this velocity will be random. And one can more or less easily make an estimate of energy injected. The energy is very ample. So the turbulence will be transonic. It will have as high velocity as it can. If it will be supersonic, it rapidly dissipates its energy. So therefore, the natural typical velocity in these conditions is the speed of sound. So in spiral galaxies, the turbulent velocities are very close to the speed of sound. This transonic turbulence, since it's transonic, it leads to a significant compression of gas. If it is compressed, it starts cooling fast, and the cooling times can be very low. Right now, Fred Jen simulates these processes with the pencil code, and cooling is a disaster. As soon as the gas density becomes of the order of 10 particles per cubic centimeter, the cooling times can become shorter than 100 years, of the order of 100 years. Radiative cooling is very fast when density is high. So fast cooling follows. So, and this, of course, can you imagine the problem for the code, right? If the cooling time is, say, 100 years, or sometimes even shorter, and you want to run your code over the physical time of 10 to the 9th years, right? So you need 10 to the 7th, 10 million time steps. Given that the dynamical scale is 1 million in terms of energy and temperature, it's quite a... So, but Fred still looks happy. So this means that cooling stars, and then you have cool clouds of interstellar gas. Then, if it becomes cool and dense, gravitational and thermal instabilities can become important. Then the clouds will become even cooler and denser. Then stars will start being formed. As soon as it becomes self-gravitating, stars will start being formed. Some of them will explode as supernovae, and we shall return back where we started. So, in spiral galaxies, because of star formation, there is this constant cycle of activity. First, because of various instabilities, stars are formed. As soon as stars are formed, they inject enormous energy into the gas. They drive turbulence. They make interstellar medium very inhomogeneous. This facilitates star formation. Again, stars are formed. It's like perpetuum mobile. Well, driven by gravitational energy, of course. The ultimate source of all this energy is, of course, gravity. It's, of course, gravitational energy, where all this energy is. So the result is a multi-phase structure in the interstellar medium. On the densest part, these are molecular clouds, where at low temperatures and high densities, atomic hydrogen combines into molecular hydrogen. Hydrogen molecules H2. And these are dense and cool regions which become gravitationally thermally unstable. This is where star formation happens. Their density is about 1,000 particles per cubic centimeter, and they are sort of 10 degrees Kelvin cool. Then there are hydrogen clouds, which are formed by compression, mostly by compression by this transonic turbulence. Their density is about 10 particles per cubic centimeter, temperature of about 100. There is diffuse warm gas. It doesn't need anything to form, because it's most probably the native gas, the matrix in which everything exists. Its density is about 0.1 particles per cubic centimeter, and temperature 10,000 degrees Kelvin. This temperature is controlled by the chemical composition mainly, and radiative cooling. It's the balance between radiative cooling and heating. And its speed of sound at 10,000 kelvin is exactly 10 kilometers per second. This is what controls the turbulent velocities. And there is a hot gas produced by supernovae, typical density of 1,000, typical temperature 1 million. If you now multiply all these numbers, you will get roughly the same figure, 10 to the third, 10 to the third, 10 to the third, more here because they are self-gravitating. So that all these phases, these three, are in pressure equilibrium. These are not because there is self-gravity. They are self-gravitating, therefore they can support a higher pressure because of self-gravity. Most of the volume is occupied by these rarefied phases. The clouds occupy negligible fraction of the volume. This figure 38 was obtained by subtracting 100 from 100, 2 and 60. These figures are of course known within a factor, not 2, maybe within 20%. So the filling factor, volume filling factor of the hot gas can range from, say, 20% to 60% of different heights. And likewise, the rest mostly comes to diffuse warm gas. Therefore, since the volume is mostly filled by these two phases, they will be our main concern. This is where magnetic fields are maintained. This is where cosmic rays propagate. This is what, to a large extent, controls the physical properties of interstellar matter. These two phases. Obviously, the hotter is the gas, the further it expands from the mid-plane. So this is the cut of the galactic disk, vertical cut. This is the mid-plane, z is equal to 0, is here. First, you have a layer of relatively cool H1 clouds. Then there is a thicker layer of warm gas of about 10,000 kelvins. And then at large heights, all the volume is filled with very hot 1 million degrees gas. Here, as you can see, there are more phases mentioned than in my table. Depending on the taste of the author, some people identify sort of maybe of 10 different phases. But I don't know. It's against my taste. I think that, for example, here, I borrowed this diagram from a book. So the author of the book preferred to identify a warm neutral medium and a warm ionized medium. What's the difference? This ionized, this is warm. The temperature is the same. So to me, it's better to be described like warm plasma whose degree of ionization increases with height. These are two different phases.
But Anwar, I mean, the difference would be that they are not like this, I think, because there would be ionized gas around which are H2 regions.
H2 regions are nothing. The size of the H2 region in this diagram is less than this red spot.
I know, but the warm ionized region, aren't they just H2 regions?
No, of course not. It's diffuse gas, all diffuse gas. Mixed together, all mixed together. There are no boundaries between them. This diagram, the author was careful enough not to show sharp boundaries. There are no sharp boundaries. Everything changes continuously. To me, from the viewpoint of physics, it's much better to combine these two
basically there will be
phases into
ambipolar
one.
diffusion in one and not in the other.
Sorry?
There will be ambipolar diffusion, for example, in the warm neutral region, but not in the
Well, if it's neutral, there is no ambipolar diffusion.
Of course, because there is ionized particle, it is not completely neutral.
But then, this is what I'm saying. Put them together. Don't separate. If I have here this air, right, has some minor degree of ionization. Should I treat separately ionized air in this room and neutral air? Of course not. It's partially ionized air.
But if the degree of ionization is high, then there is no ambipolar diffusion. So it could be different. I don't see why it should be different.
But these two phases are very, very well mixed with each other.
Yes.
It's just that neutral medium is observed in one spectral line, and ionized medium is observed in a different spectral line. Because of that, it's zoological classification, right?
Okay.
Which is based on the ways to observe rather than on the physical properties. It's zoology. So be careful if you'll be reading reviews of this topic. You will see that some authors, the list of phases which different authors introduce will be different. Don't be confused. It's just to a large extent matter of taste and matter of the position from which you approach this classification. Physically, for example, these two components are the same. It's just changing degree of ionization of the same partially ionized forms. But it's to many people it's not the case. And anyway, it's rather semantics rather than words rather than essence. So, and then this hot gas, its scale height in hyperequilibrium is very large. But for the temperature of 1,000,000 degrees, the exponential atmosphere of 1,000,000 degrees will have the scale height of 3 kiloparsecs. I remind you that the distance of the Sun from the galactic center is about 9 kiloparsecs. So if this is 9, right, 3 kiloparsecs is of that size, roughly. This is 1/3 of this distance, right? So this hot gas cannot be kept in a thin disk. It must raise up. So it raises up. Then this process takes time long enough for it to cool down. As soon as it will have cooled down, it produces very dense cool clouds of hydrogen, which, like stones, fall back down to the disk. And so what arises is something which is called galactic fountain, which is in fact sort of a convection flow, which leads to constant interchange of matter and magnetic fields between the disk and the cathode. So constant overturn of matter. And we shall see later. And these H1 clouds are readily observable. It was discovered they were discovered in the early 60s when people observed these clumps of very dense and cool gas, which all come towards us, falling on the galaxy. And in early 70s, when these galactic fountains were discovered, then it was suggested that they can be part of this fountain flow. Yes, yes, Misha.
When you say it returns to the disk, does it mean it returns to z equal to 0 plane?
Sorry, say again?
When it returns to the disk, do you mean it come below up to z equal to 0 plane?
Yes, in principle, yes. And it is remarkable, right, that the gas leaves the disk in diffuse form. It returns back in condensed form. And I will use it later, and Campbell will be, I think, using it. Imagine now that this gas has large-scale magnetic field. Right? Then this will carry large-scale magnetic field together with it, because it's diffuse. Then it will form clouds, and it will fall back. And large-scale magnetic field will stay there. So this flow can lead to quite non-trivial consequences for magnetic field. Perhaps. So this is the same galaxy familiar to us, NGC 891, which is seen edge on. Remember this one with 89 degrees. This is the image of this galaxy in H1 line. So these are the contours of neutral hydrogen. This distance is 10 kiloparsecs. You see how far the gas, even neutral gas, extends. So these are the galactic halos. They are practically directly observable, these halos. And it's too far to go back to but still, it's worth doing. Let's return back to the optical picture of this galaxy. I forgot to show you something on it. You cannot see it, right? Here, if we had a better quality image, you can see here abundant, especially in this region here. Here you can just see them, some vertical worms, dust lanes which extend perpendicularly to the disk. It's exactly these flows. This is the gas flow from the disk to the halo, which drags dust with it. It's really beautiful. If you look at it carefully, you will see these signatures of these vertical outward flows from the galaxy, from the galactic disks. Let's go back. Turbulence, a few words about turbulence. So, the first effect of supernovae is create this multi-phase structure with hot cavities, cold clouds, and warm gas in between. I said that the supernova explosions are quasi-random. About 70% of them occur in clusters, which are known as OB. O and B are the types, spectral types of the hottest and the most massive stars. And they often occur in clusters. So, well, all friends find each other and live together, right? So if there is a if there is a supernova explosion, it compresses the gas, which facilitates local star formation. Then, with a higher probability, next supernova will occur close to it, and this creates a whole cluster of supernovae. 70% of supernovae occur in such clusters. And this such a cluster, this is a galaxy M33, already familiar to us. Remember this SC type with very clumpy spiral arms, this galaxy. And this stuff, look how bright it is. The brightness of this region is comparable with the brightness of the galactic center. This is the zoom of this region. This is the region of 300 parsecs across, so 1,000 light years across, where 200 supernovae exploded more or less simultaneously. This is an example of such a OB association. So it's a phenomenon of a galactic scale. So 3/4 of the energy of interstellar turbulence is provided by supernovae. There are also stellar means galactic rotation, there's velocity shear, which contributes to turbulence. About 1/4, relatively small proportion, come from galactic winds. So the main source of turbulence are supernovae. At large distances from galactic centers, the supernova activity ends at about 15 kiloparsecs distance from the center of the Milky Way. Just because the gas density beyond that radius is too low to support strong star formation. At larger distances, for example, magnetic-rotational instability can be an important source of turbulence. But in the inner parts of galaxies, where you have these explosions are like brute force, right? They wipe away everything. Just nuclear explosions occurring every few hours around, in fact, in the Milky Way, every 50 years, one supernova explodes every 50 years, somewhere in the Milky Way. Once in 50 years. So, what happened in this supernova? First, now I want to discuss the detailed evolution of supernova. So first, it expands almost ballistically. Well, these are images of supernovae. These are historical supernovae. It's what Kepler's supernova, which Johannes Kepler was observing. This is the image in X-rays. This must be
radio.
Radio. Can't remember now. This is X-rays. This is a composite. This is radio with magnetic field orientations. This no, but I don't remember. But I told you, right? I have a good excuse to be better prepared.
24 hour notice.
So, first, immediately after the expansion, it is for about 200 years. The ejector just moved ballistically at very high speed. It's exactly what happens, but then starts the sort of tail phase, where already the expansion isn't free. And this solution of the momentum equation were obtained exactly to describe atomic bomb explosions in late 40s, early 50s, is the same Taylor, G.I. Taylor, who contributed so much to studies of the turbulence and hydrodynamics. So at that stage, the mass of the shell, which consists of the gas which was swept up by expanding blast wave, is already becomes larger than the mass of the stellar ejecta. But the internal pressure within the bubble is still so high that the external pressure is negligible. At that stage, there exists a very elegant, self-similar solution of the momentum equation, which shows that the radius of the bubble will increase as t to the power 2/5, as time to the power 2/5, time since the explosion. Kepler's supernova is here. Cassiopeia A is also a relatively young supernova. So Kepler observed this supernova to explode in 1604. So this supernova is 400 years old, right? It just entered the Sedov-Taylor phase. So this supernova just started this Sedov-Taylor phase. As the expansion continues, this is an adiabatic phase. Here, the cooling time of the material in the shell and behind the shell is so long that it's longer than the age of the supernova. But this cannot last forever. Sooner or later, cooling time becomes shorter than the expansion time. This means that there will be significant energy losses. Here, the energy is conserved. We can neglect radiative cooling. So it's an adiabatic evolution. But sooner or later, radiative cooling will become important, and then energy will no longer be conserved. But instead, momentum will remain conserved. And then there will be the next stage, which is known as momentum conserving stage, which lasts for 100,000 years. And there again, you can solve the equations of motion, and then you will find that roughly the radius of the supernova varies as time to the power 1/4. So instead of Taylor phases for 2/5, 4.4, and here's 0.25. Slight change in the expansion law. So this transition to this phase happens when the supernova is about 35,000 years old, and its expansion velocity is about a couple of hundred kilometers per second. And then at still later stage, when the age of the supernova remnant will be of the order of 1 million degrees, its internal pressure will become comparable to the external pressure, and it will start disintegrate, just falling apart, like we have here. This is a shell of a very old supernova remnant. You see all these local shock fronts everywhere, but overall, this shell starts disintegrating. This exactly will be the time when the remnant will start injecting kinetic energy in the surrounding medium. As long as it expands supersonically, the gas in front of the shock front cannot know about the approaching shock, right? Because it's a supersonic expansion. As soon as the expansion velocity will drop down to something like the speed of sound, then there will be perturbations spreading around the supernova remnant. This is when the turbulence will start being created. So, what I wanted to do here. Okay, let's skip it. Just giving a few numbers. So, and then this turbulence is very, well, not easily, but still observable. If you calculate the size of supernova shell when it comes to pressure balance with surrounding medium, you will get the diameter of the shell of about 50 to 100 parsecs. And it's exactly, it's just similar to what is observed for the correlation length of random motions in the interstellar medium. And since the energy injection is so high, the turbulent velocities will be close to the speed of sound, 10 kilometers per second. This is the very well known, famous diagram, which is known as big power law in the sky. These people, Armstrong and authors, Armstrong, Cordes, Rickett, there were 3 or 4 authors here in this very really famous paper. They collected all available to them data about random fluctuations in the stellar medium and converted them, recalculated them into the density fluctuations. Obviously, density fluctuations and velocity fluctuations are related to each other. And plotted the result in one diagram. And clearly, all these diverse results fit one single power law. And the slope of this curve is log scale. It's compatible with Kolmogorov spectrum. Well, the accuracy isn't that high, so I'm saying carefully compatible with Kolmogorov spectrum. But look at the range of scales. This is the wave number, log of wave number, from -18 to -6. 12 orders of magnitude. 12. Or even 10. Or 10. 10 was from. It's a fantastic thing. 10 orders of magnitude in terms of scale, one single spectrum observed in such a wide range. Of course, the physics of turbulence over this enormous range of scales cannot be the same. For example, here, the collision length, these are meters, that is 16th. The mean free path in the stellar medium is somewhere here. So it's clear that here the turbulence will be collisionless, it will be plasma turbulence. At larger scale, it's MHD turbulence probably. But what follows from this diagram is that this turbulent energy, being injected at these scales, that cascades down, is transformed to a different form, for example, into the form of plasma waves somewhere here, but it's not lost. It continues the turbulent cascade down to thermal or viscous scales. I'm not aware of any other example of turbulent spectrum of this sort. 10 orders of magnitude. So, the interstellar medium in spiral galaxies is rotating, is stratified, involved in random motions, is partially ionized. You can't imagine a better setting for dynamo action. It's just perfect. A few words about elliptical galaxies. So these are several images of elliptical galaxies. E1, E0, E5 is more elongated. And this is how the classification is defined. This number and here, 3, 1, or 0, or 5, is just equal to 10 times 1 minus B over A, where B over A are the axis, or semi-axis, of this ellipsoid. This is how this looks. So this classification is very straightforward. They are structureless. They don't have overall rotation. So interstellar gas is quite uniform. It can be taken in X-rays. It's just very hot, rarefied, quasi-homogeneous gas. There can be a fluctuation dynamo there, but hardly very important. This is an image of one of the giant elliptical galaxy M87 in X-rays and stars. So these white are stars, and this reddish glow is the X-rays, the distribution of the gas. These are examples of observations. This is how a galaxy looks in optics. So this is distribution of stars, and this is distribution of gas in the same galaxy. Distribution of gas. So you see that, well, not very exciting to my taste. Galaxy clusters are much more interesting objects.
Well, we don't know so much about the elliptical magnetic fields, right? So I keep asking,
it is known that they do exist, because they can be observed indirectly. There is very little direct observation evidence of the magnetic fields in elliptical galaxies. But indirect evidence is there. So there must be magnetic fields there.
The land guarantee effect and things like that.
Yes, depolarization and stuff.
But these are all where there is already a radio galaxy also sitting out there.
Yes, if there is many of these active radio galaxies are elliptical galaxies, but they have an AGN, an active galactic nucleus in the center. which makes life entirely different. This massive
So
black
normal
hole is
ellipticals.
normal ellipticals
We don't know.
just graveyards of stars.
No, because, see, I mean, according to popular theories, let's say this merge to make ellipticals, some theory. But this has a magnetic field. It has made a dynamo and then you merge it. So,
There will be turbulence,
yes,
and turbulence will destroy this magnetic field quite quickly, won't it?
as you said, okay, we should go ahead.
Difficult to say, but so galaxy clusters. There is no overall rotation. They contain a few thousands of galaxies within the region of about 500 parsecs. So the size of a normal spiral galaxy is sort of 20 parsecs. The size of a cluster is 1,000 kiloparsecs. So 20 versus 1,000. This is the range of scales we are talking about. The velocity dispersion of galaxies is close to the virial velocity. It's about 1,000 kilometers per second. The gas between the galaxies is hot. Not surprisingly, right? If there is something which moves at such a crazy speed, it will of course heat the gas, and this is roughly the virial temperature. The speed of sound at these temperatures is similar to 1,000, close to 1,000 kilometers per second. The density of this gas is very low, 10 to the minus third particles per cubic centimeter. It is more or less readily observable in X-rays. And it was one of the great discoveries of X-ray observatories. You cannot observe X-rays from the Earth's surface because the atmosphere is not transparent to X-rays, like our bodies, right? So the first X-ray observations were possible from the orbit, from satellites. And very soon, very quickly, it was discovered that in fact these galaxy clusters are not relaxed steady-state systems. They are still in the process of formation. And this was a huge surprise to everybody. And I will show it to you. So this is a nearby, relatively nearby, rich cluster of galaxies. So this is a composite picture. Yellow are galaxies, as observed by the Hubble telescope in optics, and purple is the X-rays. So you see how many galaxies, this spot is a galaxy. Look here, this is an elliptical galaxy. This is a spiral galaxy. Another spiral galaxy somewhere here. This has a bar. It's a fantastically rich picture. Look at these amazing things. Look at these arcs. Do you see them? This one, and this arc, and this arc, and this one. These are not the results of bad cleaning of the lens, you know. Oh, well, it relates to a lens, but this is a result of gravitational lensing. These are the images of background galaxies, which have been distorted by the gravitational field of the cluster. So these are gravitational lensed images of remote galaxies. And from the appearance of these arcs, you can find out the gravitational field of the cluster, which is an amazing thing to do. So from this, you can determine how the gravity is distributed in this cluster. So let's see if, no, I have to click here. So purple is the X-ray gas, yellow are the galaxies. So these are the galaxies, and this glow, diffuse glow, this is just X-rays. This is how this cluster looks in X-rays. So this is distribution of hot gas. This is the distribution of hot gas. Well, looks absolutely relaxed, right? And still, this is the process of merger. And this can be seen in this cluster. From the, oh, look at the arcs. Look at the arcs here. And this can be seen from the distribution of temperature of X-rays. It's rather patchy. This is a fantastic, famous example of this merger. What is shown here, again, an overlay of 3 images. These are, again, the Hubble optical photograph of this cluster. This is the name of this cluster. It looks like telephone number, right? So this yellow are all galaxies. You see this barred galaxy
It's
here.
called the bullet cluster,
No, it's not bullet cluster. It's
No?
a different one. Different one.
right?
Because it's not a bullet cluster.
Oh, okay.
So the yellow are the galaxies. This purple is the gas seen in X-rays. So it seems that if you forget about this blue, I will explain what is blue is in a moment. If you forget about blue, this seems that this gas sits in the center of the cluster and everything is nice, beautiful and relaxed. But this blue is the distribution of the gravitating mass, which was obtained from this gravitational lensing. Look at this arc. This is a small arc. There are more arcs around here. So there is also widespread gravitational lensing in this cluster, which allowed people to calculate the distribution of gravitating mass. And blue shows the distribution of the gravitating mass. What we see here is a collision of two clusters in the sky plane. Two clusters which consist of stars and dark matter collided with each other, passed through each other, because galaxies and dark matter are collisionless, so they just pass through each other. But the gas, which was coming with each one, is collisional. So the gas stayed in the middle, and the mass continued. The result is that this gas is just stuck in the middle after the collision, and the many dark matter and galaxies proceed beyond each other. Obviously, they probably are on the orbit, it will continue. So this is an example. Now it's a simulation of such a merger of galaxy clusters. I'm sorry for all these movies, but I couldn't resist the temptation.
Oh,
So it's the model of a merger of two clusters of galaxies. Nothing surprising, basically. What else can you expect? So probably many clusters which you observe are about sort of this stage, when they're still, the merger hasn't finished, but they are already four more or less well-defined single cloud. That's it today. It's for today. I have done what I wished to. I'm really pleased. I was afraid that it would be too slow. This is the end of the day. Thank you. And look at the time.
And questions, please.
Yes, please.
Are there radio evolution or
Yes. I will be talking about this, tomorrow, right?
Yes.
Tomorrow. But I will be still, again, better prepared for tomorrow still. So, but I will discuss now radio observation. I will now discuss various observations of these objects. How we know what is the velocity field, how we know what is the magnetic field. Tomorrow, with pleasure. Matthias?
Yeah, you were talking about these galactic fountains,
Mm-hmm.
which seem to be permanent losses, or seem to create a permanent loss of magnetic field on the disk, because it is transported upwards, but not transported downwards.
This is what I think happens, yes.
Yeah. Is this really included in the dynamo models?
Now, yes, now we are using it to remove helicity from the disk. We in early 90s with Axel, we had papers about mean field dynamos with such an outflows. Of course, such an outflow, if it's too strong, it will destroy any dynamo interaction, right? If the time scale will be shorter than dynamo time scale. Obviously, it can be destructive. But now, with this helicity balance, it seems that it can help. And there was a paper with Axel and with Kando, where it seems that if you include this outflow, it starts removing helicity and then helps the dynamo. So then, if the outflow velocity increases, first the dynamo becomes heavier until it becomes really unheavy, and it goes down.
you will discuss this, I will be also putting it.
No, I will not be. It will be. And Andrew Smith is now, we are trying to apply with Andrew Smith this model to real galaxies just to see if it will agree with what we observe. It's that because now these outflows can be related to star formation rate, to the depth of a potential well. These are all observable quantities, we know that. So we can check if the predictions of this model will agree with what is observed. It can be really interesting, and I hope that with them very soon we shall start getting interesting results. Well, both ways it will be interesting, right? If the model will be confirmed, fantastic. If it will be disproved, okay, fine. Well.
So you show these worm-like structures in the picture, which indicate that the dust is taken together with the gas.
So
this made the impression to me that this outflow, this fountain, are not continuously moving, but more or less locally.
Yes.
So the transport of the magnetic field wouldn't be, in some sense, homogeneous, but there is locally concentrated.
Agree. But this, with Andrew Smith, we cannot address this because our model will be rather parameterized. But with Fred Gent, who is modeling a box, local box, where he injects thermal energy just to model all this activity. In that model, we shall be able to address this question. We shall be able to see how inhomogeneous are these. So there will be a computational box. We started a few years ago this work with Mari, Korpi, and with Axel. Now Fred Jen continues it, and also Mari is involved. Then we have a box which is 1 kiloparsec by 1 kiloparsec horizontally. So it's 10 turbulent cells by 10 turbulent cells. So 100 turbulent cells in the area. And it has the height of 2 kiloparsecs on one side. So 4 kiloparsecs both. And then you start with hyperequilibrium of the gas of uniform temperature. And you start injecting at random positions, positive random positions, thermal energy in this amount. And then all these horrible events evolve in front of you. I think that Fred will be able to present a talk based on his first results from these simulations. And then we shall be able to address these questions. Then we shall be able just to really average the outflow velocity just by calculating.
The Gressel simulations also show
Similar.
Yes? About the dark matter, I mean, it's there and it's giving a gravitational field, which you can see. I mean, you're assuming, presumably, that it's just sort of sitting there. Is that not interacting with anything else? Is that?
Yes. So whatever it does, then it becomes an important what it does. Does it rotate or does it not?
Right.
Does it have to some random velocities or does it not? Because it doesn't interact with anything.
Yeah.
It only creates a potential gravitational well for you.
And you think it's more or less spherically symmetric, is that right?
Probably. Yes. At least.
But gravitationally back.
Yes. These galaxies are gravitational. Yes. Probably. What Kando would know more about that.
Firstly, it started with weakly interacting, so it's almost collisionless.
Yeah.
And simulations show, of course, variety of shapes. It may be triaxial, in which you somehow form a disk. But where the disk is formed,
So it's going right over the halo region of the spiral.
I mean, it's much bigger because it's like
The other way around.
scale is like 100 kiloparsec, whereas the disk is only tens of kiloparsec.
Right, yes. So it's going right
Yeah.
way into the halo.
Yes.
Yes, please.
So you show that the plasma is mostly in the collisional state.
In the hot gas phase, it is collisionless, but the other phases are strongly collisional.
So
The mean free path in the warm gas is 1/1000th of a parsec.
So you expect the magnetic field to be amplified in the collisional
Yes,
part?
yes, yes. For several reasons. Mainly because the hot phase, it is in an unsteady state, just because it's so buoyant. The volume elements in the hot phase, they don't stay long within the disk. They rapidly leave the disk. Therefore, if you make some estimates, it's clear that their lifetime within the disk is shorter than the time scale of any dynamo action. Fluctuation, forget about the mean field dynamo action, it's much slower. So most probably, this hot phase just drags away whatever magnetic field it can capture in the disk. But most of the interesting events occur in the warm gas. which is just like a fabric within which all these events happen. And importantly, it's impossible to say, of course, but since the volume filling factor of the warm gas is larger than about 60%, probably it forms a percolating cluster, so it's it will be a simply connected region. So you can imagine that we look at this interstellar medium from afar, right? Then it's important how everything is distributed. Imagine that this is a matrix of warm gas, and there are cavities of very hot gas, right? And then there are somewhere very small, dense clouds. Now I want to populate this with a large-scale field. Obviously, these regions are disconnected. I cannot put there large-scale field. But this region can contain a large-scale field. It needs to be simply connected. It's quite a subtly interesting thing. So the worst situation is if neither of the phases forms a percolating cluster. So, for example, if I have something like that, and I want to embed magnetic field in this direction, neither of the two phases can host a large-scale magnetic field directly that way.
But why can't it just penetrate?
How? The density is different here, by factor of 10 to the third. So imagine that I have a disk like that, right? Magnetic lines like that. And then here I explode a supernova. What will happen? How it will penetrate? Of course it will do it differently. And there will be a hole in it. How it can penetrate? It's a blast wave expanding supersonically. Diffusion time to penetrate is measured in millions of years if you are lucky.
No, because basically the hot gas is coming also from the interstellar medium,
Yes.
which hosted the magnetic field. So there must be some flux going through that. Which you cannot just
But this again, it's a shock wave. So you imagine that magnetic line very carefully doesn't break, it doesn't go like this. Of course there will be some magnetic lines.
No, it has to go, but only thing that the field may get diluted because of flux field.
Of course it is.
But there must be lines going through,
Some.
because it's after all was the interstellar medium which got heated up through the blast wave.
So if I zoom this picture, this is my shell, right? What I imagine would be the following. Most of the lines will go like that.
Yes.
And one,
Yes. But give me one at least, no?
no, I can tell you how many. It's rho to the power 2/3, right? Rho to the power 2/3, 10 to the minus 3, 100. 1 out of 100 I allow you to move like this.
Yes.
1 out of 100. Not more.
Okay. No, because that I got worried about. This I'm happy. You give me 1 out of 100 I'm happy.
1 out of 100.
Any other questions? Okay, we have coffee now, but
Thank you.
before that,